Welcome everyone. This is a presentation on our control theory project. The title of our presentation is Animation of Collision of Two Balls on a Curved Surface using MATLAB and Simulink. You can see the name of the group members. This is for realizing a curved surface. We approximated the surface like this because the total curved surface is very difficult to realize. The length of each surface is 10 units. Means this the distance of this surface from here to here, and we used some more surfaces which is not shown here. Now s is the displacement of the balls along the length of the surface. It is the variable by which we give the position input. Means here s is equal to 0, here s is equal to 5, here is equal to 15, because each of the surface is the 10 units. So this is pretty much self-explanatory. For realizing the collision, we use this spring equation. Here k is the spring constant and d is the distance between the centers of two balls along the surfaces, along the surface, because if the size of the balls are different, then just only detecting the distance of the centers will not give us the exact result. So we have to modify the equations. K is the spring constant, as I said, and Fc is the force due to the collision. For realizing the friction, we use this damping equation. Here B is the damping constant and V is the velocity of the balls, and this is the gravity equation. Here M is the mass of the ball, theta is the horizontal alignment, like the previous slide. Here you can see some of the surfaces are aligned with the horizontal line, and theta is the angle between the horizontal line and the surface, and the rest of the things are just elementary trigonometry. You can see M and the mg, or the gravitational force, will work towards this line, and along the surface we use the component using along the surface by taking the sine theta of the alignment angle. And this is the calculation of the position coordinates x and y of the ball from the position of the ball on the line defined by s. As an example, if the ball is here on the surface 2, we have to use these equations to translate the positions of the ball from the value of s. Here you can see we have to add 5 and then subtract 5 from the value of the s and multiply it with cos theta, the alignment of the surface, the alignment of the angle of the alignment of the surface. And same goes here with this rest of the equations. This is for the surface 3, and this is for surface 4, and this is for surface 5. We set the value of s here is 0 because we wanted to simplify our equations, just to give the mirror values, like the value of s and the rest of the coordinates here and here are the mirror. Same goes for surface 3 and surface 5, surface 4 and surface 2, and so on. Now let's watch the demo, I mean the animation of the collision. Here is the block diagram, the whole block diagram of the animation. Here we can give the frictional constant, the initial positions. If you remember, minus 60 means the value of s is minus 60, means minus 60 is somewhere out there, and position 2 is the ball of the position 2. It is a positive value, so it will be in the right side. First, let's watch the animation without friction. Here you can see the initial positions of the ball. Let's run the simulation. There are some rendering problems because we are running this Camtasia and MATLAB together, so our PC goes slow, so please bear with us. Here you can see without the friction there is no energy loss, so the balls are with the equal values of mass, so they go back to their initial position after each collision, because they come down from the same height with no energy loss. They have to go to their initial positions. Now let's add some friction. Let's put point 1 here. Reload the file and run the simulation. If this is getting boring, so please bear with us. Now we can see, as there is friction, so there will be energy loss in every displacement of the balls, so eventually they will come to rest. So they are slowing down as expected. Now let's change the size of the balls. Now we can see two different size balls, but our equation will still detect the collision correctly. As this ball is heavier, the force acting on it is lesser than this ball. On every collision, this ball gives more force to this ball. Okay, that works fine. That sums up this presentation. Thanks for watching.